Hi, welcome to my talk today about vehicular source tracking and near-surface characterization with 6 degrees of freedom point measurements. My name is Shihao Yuan, and I'm presenting the work that I've done with my collaborators Felix Bonar, Andres Boza, Joachim Wassermann, and Heiner Igel at the University of Munich. Seismic-based bearing estimations gaining increasing interest in surveillance systems because of its broadband sensitivities to not only natural sources like landslides, but also various anthropogenic ground motions, such as human and vehicular movements. Determining the source directions of incoming seismic waves is commonly achieved by beamforming or frequency wave number analysis. The basic idea behind them is to extract the coherent seismic energy that propagates to a seismic array according to some trial slowness model. Seismic array measurement has an aperture-dependent resolving power. In practice, this geometry and the number of seismometers of an array are determined by the scientific purpose and economic limits. Sometimes the deployment and maintenance of a seismic array can be logistically very challenging. Besides array measurement, polarization analysis of a single triaxial seismometers can be also used to estimate the direction of arrival. Based on hodograms, that's to see the particle motion trajectory, one can derive the propagation direction from those linear polarized events. It basically relies on single-mode variations. If multi-type of events are present within the chosen window, then this assumption is not valid, and the analysis may break down. Therefore, classic polarization-based propagation direction detecting algorithms are most successful on the cleaner first P-wave arrivals. Furthermore, a single triaxial seismometer does not provide sufficient information to decide between two possible incoming directions related to a 180-degree rotation. Either array measurement or classic single-station measurement rely on translational motions that are recorded by seismometers. Ground shaking caused by natural or anthropogenic sources can also generate rotational ground motions, which represent particle motion around a certain axis. With the development of new seismic instruments in recent years, such as optical-based sensors, rotational motions from earthquakes to ambient noise can be also accurately observed. In this study, we would like to combine translational and rotational observations to a single station 6 degree freedom observation and apply it to vehicular source tracking and near-surface characterizations. We will show how this 6 degree freedom point measurement can potentially integrate the functionality of both array and classical single-station measurement and overcome their deficiencies. Rotational motions are essentially the core of the translational Wavefield. Because of the core operations, rotational sensors can be treated as polarizing propagating filters, which will naturally filter out or separate the different type of seismic waves according to their polarization and propagation features. In general, there are three categories. For P or longitudinal waves propagating isotropic mediums, they won't be recorded by rotational sensors since they are curve-free vector fields. For SV and Rayleigh waves, as they polarize in the vertical plane, they will be isolated into horizontal rotational components. SH and LOVE waves will be exclusively recorded by the vertical rotational component as their particle motion and the propagation direction are contained in the horizontal plane. Such Wavefield separation of the 6 degree of freedom point measurement will directly benefit the source bearing estimations. Let's take the SH or LOVE wave as an example. In Figure A, we present a synthetic teleseismic event where the zoom-in plot selects a small portion of the LOVE waves. The right curve represents the vertical component of rotational rate, and the changing black curve represents a transverse acceleration rotated according to a series trial back-azimuths as shown in Figure B. Considering that the transverse acceleration and vertical rotation rate basically result from the same portion of Laue waves, zero-like cross-correlation coefficient should reach a maximum if the trial back azimuths coincide with the real one. Figure D shows how these correlation coefficients vary with the trial back azimuths. The 180-degree ambiguity can be resolved because transverse acceleration and vertical rotational rate should be positively correlated. Apart from Laue waves, SV and Rayleigh waves can be also used to estimate source directions due to the fact that they are isolated in horizontal rotational components. Without the interference of direct SH type of waves, the source back azimuths can be retrieved through classical polarization analysis of pure horizontal rotational components. The 100 ambiguity can be resolved as well by comparing the translational and rotational components. Both correlation-based and the polarization-based method rely on ice wave and surface waves, so they are complementary to the classic P-wave-based method. The 6th degree of freedom measurement is actually not only applicable to static sources, but also moving sources with sliding windows. After retrieving the source back azimuth information, we can rotate both translation and rotational component into radial and transverse components. Based on the plane wave assumptions, the Rayleigh and Laue wave phase velocity can be estimated through those two well-known formulas, respectively. A consequent frequency-dependent behavior of these amplitude ratios may be expected due to the dispersive characteristic of surface wave. In addition, the sensitivity of this amplitude ratio-based quantity is theoretically equivalent to the differential sensitivity of its numerator and denominator. That will make the derived phase velocities provide a more concentrated constraint on the structures near the measuring point. Now let's move on to the real application of the 6th degree of freedom point measurement. In combination with the classic broadband seismometers, the newly built ring laser gyroscope at the Geophysical Observatory Fürstenfeldbruck near Munich allow us to record a highly accurate and broadband 6th degree freedom ground motions. The rotational sensors is denoted by the blue dashed triangle in the zoom-in plot, and seismometers are marked with red triangles. All seismic stations, including the rotational sensors, are in the vicinity of the highway, indicated by the green line, except one station, TON, which is closer to the railway, denoted by the blue line. This is 1 hour continuous recording of seismometers during the midnight. We notice that similar events are recorded at all stations except at the top one TON stations. This is simply because the TON station is adjacent to the train track, while all other stations are closer to the highway. So the signal sources are distinct. And the train signals are not visually as evident as car signals for those stations near the highway. To select the frequency band for tracking moving traffic sources, we first pick 2 chunks of data within the right dashed square and check their time frequency characteristics. The top panel represents train-related signals recorded at the stations TON and FFB3 and their corresponding spectrograms. The arrival time difference of the peak ground motions at 2 stations, which is approximately 30 seconds. This can be attributed to the traveling time of the freight train from one nearest point of the one station to the others. The waveform amplitude at station FFB3 is not as visible as that at TON, presumably due to the faster attenuation of the high-frequency contents. However, the lower resonance frequency at FFB3, for instance, 5, 9, 12, and 14 Hz are kept and are consistent with those at station TON. Some monochromatic spectral lines around 16, 26, 33, and 45 Hz appear merely at the TON station, which are possibly induced by the railway electrification and nearby and its harmonics. The bottom panel describes the car-related signals recorded at the station FFB2 and FFB3. The common features in the spectrograms shown in figure C and D imply that both signals result from the same sources. The absence of the higher frequency contents, especially above 20 Hz at station FFB2 compared to FFB3, is mainly due to the attenuation similar to the trend signals recorded at station FFB3. For the following analysis, we will band pass our seismometer and rotational recording into 3 to 15 Hz. First, we would like to apply the cross-correlation-based method with law waves to track the moving vehicles. The top 3 panels denote the 2 horizontal accelerations and vertical component rotational rate. Considering the relatively low location of the 6 degree of stations and the highway shown in the left-hand side, back-azimuth variation of the inbound vehicles are expected to decrease from 100 to 0 degree and then keep decreasing from 360 degrees to 300 degrees approximately. The outbound ones are just the reverse. From figure D and E in the right-hand side, we can clearly identify the expected bidirectional varying patterns from the estimated back-azimuth as a function of time. Note that we only keep the back-azimuth denoted by the dots black dots in figure D with a cross-correlation coefficient higher than 0.4, just to avoid some interfering signals with low signal-to-noise ratios. In comparison, we have also estimated the back-azimuth variation from the frequency with number analysis in figure E using the surrounding seismometers. It shows that the 6 degree of freedom point measurement using law waves agree well with that from the array measurement. For the zoom-in plots of the 2 selected time windows within the right square in figure D, we can calculate the moving speed of the vehicle through the ratio of distance and time over a certain back-azimuth variation range. The estimated average speed in figure F is approximately 90 kilometers per hour, and the one in figure G is approximately 65 kilometers per hour. Both are empirically reasonable estimates at the period of night. Unfortunately, the horizontal rotational component with the high signal-to-noise ratio is currently not available as an instrument is under maintenance. However, we can test the polarization analysis with pure rotational components using array-derived rotation in the following slide. As rotational motions are essentially the spatial gradients of translational motions, we can therefore calculate them indirectly from a small seismic array. Regardless of its band-limited accuracy, array-derived rotation provides an independent way of validating rotational motions directly recorded by rotational sensors. To verify the proposed 6 degree freedom point measurement, we first calculate the 3-component array-derived rotation for the reference station co-located with the rotational sensors from the surrounding stations. Then we apply the same processing strategy onto the array-derived rotation and acceleration records. As shown in figure D and E, the estimated back-azimuth variation from either SH or law waves or relay waves are not only self-consistent, but also in good agreement with those from the 6 degree freedom point measurement. Finally, we can use the estimated source directions for each time window and rotate the translational and rotational motions into radial and transverse components so that we can extract the dispersion curves based on the amplitude ratio formula we introduced before. Here, we only show the estimated log wave phases velocities at each narrow frequency band. The frequency band is chosen between 2 and 20 Hz simply based on the spectral energy that shows up in the seismometer and rotational sensors. The analyzed signals are basically assumed to be dominated by fundamental mode surface waves. However, higher mode can appear and interfere with the fundamental mode. Thus, the estimated phase velocities can be very scattered as shown in the upper panel with a short limited period of data. After processing a longer period of data, here, in this example about 1.5 days recordings, the stacked result shows a much more stable and evident dispersive phase velocities. 1D velocity models can be inverted afterwards to characterize the near-surface structures. In summary, we have shown that the 6 degree of freedom single station measurement can be used to track moving vehicular objects. It is actually not limited to traffic noise monitoring. It can be also potentially applied to other natural sources. Compared to classic surface wave measurements, the dispersion curves extracted using the 6 degree of freedom measurement from either ambient noise or any other ground motions has a more localized sensitivity and will provide more concentrated structural constraint beneath the receivers. This is particularly useful if we need to conduct site-specific near-surface characterizations and near-risk analysis. The array-like functionality of the 6 degree freedom point measurement makes it superior, especially when seismic arrays are difficult to deploy due to unfavorable environments such as ocean bottom, urban area, or mountain areas, or other planets. If you have any comments and questions, you can contact me through the following email. Thank you for watching the talk, and I would also like to thank my collaborators and the session conveners. I look forward to seeing you in the live sessions on Wednesday, December 15th. Thank you.